Alright, so in this example, we're going to look at a scene classification or scene labeling task using CNNs and specifically implemented in PyTorch. We're going to look at this data set specifically, so this SAT-6 data set, which is effectively a large set of 28 by 28 pixel 4-band or color infrared image chips derived from the National Agricultural Imagery Program data set. In which 6 categories or classes are differentiated. You can get this data from this page from the Louisiana State University. The data are actually in a MATLAB format, so I found that was kind of difficult to use in R or Python. So I ended up downloading the data from this Kaggle page, where the data are provided in a CSV format, which I just found easier to use. So whatever you're comfortable with, there's a couple different versions of that data available. This data was originally presented in this paper by Bissot et al. So DeepSat, a learning framework for satellite imagery, and you can see here that they've ran experiments with a 4-class version of the data set and a 6-class version of the data set. Again, we're using the 6-class version, and you can see some of their reported accuracies there. Okay, so again, similar to our other examples, we're going to work predominantly in R and Python using RStudio as our IDE. So I'm going to shut this off and move over here to RStudio. Okay, so the first thing we need to do is make sure we have our R library, our Python environment linked up in R. So I do that with the reticulate package here, and again I've already set up an environment, and I showed how I did that in a separate video for this specific task that has all the required libraries and the correct versions and whatnot. So this is PyTorch SB. So we pointed at that, and then pyconfig prints that configuration to make sure we have what we need. And as you can see here, we're now linked to that library. Again, sometimes if this fails, you might just want to restart your R sessions. Just go up and do session, restart R, and that should fix that issue. Okay, so once we have that, once we've connected to Python, we're ready to actually prep our image chips. So what I'm going to show you is the way I did it, which was in Python, but you could probably implement this in R if you'd like. There's also other ways to do it. Like, I'm actually creating all the image chips here as little PNG files, but you could actually run this without actually creating the images. Okay, so we're in here in Python now, so I'm just going to load in some libraries: OS, NumPy, Pandas, Matplotlib, scikit-learn, and then Torch, obviously, and then image.io. So image.io and SK image are used for reading in the image data specifically. Okay, so next thing I do here is define a function, and what this function does is it converts the annotations from like a one-hot encoded format into a single column with an integer representing each category from 0 to 5, so a total of 6 classes. Let's have a look at this data set before we do that. So I have this in this archive folder here on my local machine, and what we're working with specifically is this y test, y train. I'm going to open up the y test because it's smaller, so you can just see what that looks like. So you can see here, this is a CSV file with no header, and there are 1, 2, 3, 4, 5, 6 columns, and whatever the correct classification for that chip was is coded to 1 in that specific column and 0 to all other columns. And this isn't really the form that we need this data in for this learning process using PyTorch. So what we do here is we just extract out the column number that has 1 in it, or the highest value, and return that. And that's what this anoprep tool does. So it accepts a DataFrame in, DataFrame out. Well, I guess technically this is actually accepting the CSV in, CSV out. So then I define those variables. I read the input table using pandas and read CSV. Note here I set header as the none because there's no header. I changed the column names to 0, 1, 2, 3, 4, 5 because those are the values I want to get in the final output. And then this labels.id max axis equals 1. What that's doing is pulling out the label or the column name, which is 0 through 5, 1 of 0 through 5, for the one that has the maximum value in that row. So that will be the 1 versus 0. And then what we end up with after that is this single column of data. And then we push that out to a new CSV file. So that's the function. We don't need, I'm not going to run it because it takes some time. But once we have that function, we just read in the data and then export out copies of the data. So let me show you what I ended up with here. So again, these were the inputs that I got from that Kaggle page. We're working in this chips2 folder here. So I'm just going to open up the test one. So what this did was converted it into a column with the index for the correct classification in there. So 0 up through 5. So that's one hot encoded back into just like a single column where a index is assigned to each category for a total of 6 categories. Okay, and then the next thing I do is define a function to generate the image chips from the CSV file data. And here's what we're doing. So first thing I do is read in the CSV data that stores the image. And then I pull the shapes, so the number of rows and columns to get the shape there. Or sorry, from the shape I pull the row and column lengths. And then for each row in the table, where each row represents an image, I run through this process. So I pull the row at the current, so it's a loop, so that at the row I, so it starts at 0, column index 0, convert that into a NumPy array, then reshape it, because this is just one long vector, so I wanted to reshape it into 28 by 28 by 4, and that's because these are image chips of 28 height width and then 4 channels. Then I create a name, which is effectively going to be the index, so 0 through the number of chips, plus the file extension. Here we're doing PNG, and I add on to that the path that I want to use. And then lastly, I do imsave, which saves that image out to an image file. So 4-band PNG files, 4 channels. Okay, just so I don't know that I want to open this because these are gigantic and they take forever to open. But I'm going to try to open one of these real quick so you can see what it looks like. Effectively, how this data is formatted is it's just one large CSV file where each row represents an image and each pixel location is in one of the columns. So it's 28 times 28 times 4 for each row. So that's why these data sets are pretty large. So effectively, we're representing that image as just like a vector in one dimension. And then we're using NumPy here to convert it into an array with the correct shape. Yeah. That's taking a while to load, so while that's loading, let's just go back to this and we'll talk. Okay, and then next thing I do is I actually generate the directory. So I've created this chips2 folder. Within that directory, I create a train X and a test X where the images will be stored, and I use os.make directory here to make those subdirectories. And then lastly, I apply that CSV to image function on the training set CSV file and the test set CSV file and write it out to that folder, either the train folder or the test folder. Okay, and that's effectively it. Let me show you what the output of that is. So this is the chips2 folder, and again, those are the subdirectories that we created. So in this train X folder, we have all of these little tiny image chips, 128 by 28 by 4 channels. And you can see there's a total of 324,000 image chips to train on. And then the test X is the test set, and you can see it's the same thing, but there's 81,000 images to train on there. Let's see if this is loaded yet. Almost there. Again, these are really large CSV files, so they're kind of hard to read. So again, each of these rows represents an image, and you can see there's a ton of columns there that represent all of the pixel values. So again, 28 times 28 times 4. So let's close that down. Okay. All right. So anyway, now we basically have our training data prepped, both the labels, the Y data, and the images, the test data. Again, you could have done this without actually building the images. Like we could have created the images like in the data set or when we define that for PyTorch, but I just wanted to produce the images. So that's how I did it there. Okay, so anyway, that's the prep. And the next step is to actually start to build our model. So that's this SAT-6 example file. So let's step through this process. Okay, so again, I put some links in here to some of the libraries that I used examples that I used to build this out. And then again, we're just loading in our libraries here that we need. Note I am using Torch Vision to do some data augmentation, Rasterio to read in the raster data. A lot of the other things here are just coming from Torch. See, open computer vision, OS, and then our standard data science stuff, NumPy, Pandas, scikit-learn. Okay, so the first thing I do is I change the directory to the chip2 folder where all my image chips are stored in those subdirectories. So I'm just going to run these so we can see that. The next thing I do is test and make sure my GPU is available. So again, it prints back true. I have one GPU and then the GPU name there. Okay, and now I'm reading in the training test data. I actually don't need the test data for this example. I'm just using the training data, but I just went ahead and read them both in. So again, I'm just reading those in with pandas. And then note that there's no separate validation set to test the model at the end of each epoch or iteration over the training data. So what I do is I split the training set into separate training and test sets. So what I'm doing here is I'm reserving a proportion of 0.2 or 20% of the data for testing, and the remaining will be the training set. So effectively, now that we have 3 data partitions, training and validation, which came from this training set, and then the test set, which was already divided out. And then after that, I just get the lengths to make sure it makes sense. So here you can see we have 259,200 examples for training, 64,800 examples to validate on at the end of each training epoch, and then we have our 81,000 that we'll use for testing to the final model. Note this random state, what that's used for is to make the randomness reproducible, so you get the same splits each time, and that's just, again, for reproducibility. It's not required. Okay, now we're gonna subclass the Torch Dataset class to load in our data as we for this specific task. Okay, so again, the dataset classes have to have these 3 functions or methods. So the initiate, the get item, and the length. Okay. So what we're going to feed it is a data frame. So we're going to feed it a data frame, and we're also going to feed it a directory of where the image data are stored, and then potentially some transforms. So here we initiate all those variables and the init there, and then get item is where most of the work is done here. So this is again for how you would get a single sample from a row in the data frame. Okay, so we basically would pull the row at the given index, so that's the row index, and then we're looking at the data in the second column, which in this case is the label, right? So if you remember that folder, the first column was like the row number, and the second column was the index. If you remember, Python starts indexing at 0, so this is the second column. So that pulls the label data, and then I open the raster data with Rasterio, as opposed to opening it with like Torch Vision or Scikit Image or OpenCV. I did this because it was for band and it just seemed to work well this way, but you could do it another way. So basically, all the images have the name of the index. So it was, for example, 0.png, 1.png, so on and so forth. So basically, to get that, I'm just grabbing the directory that I provide. I'm adding one to it, the index, and then lastly the extension, and that reads the image in as a geospatial raster, and then it opens the data, and then read converts that into a NumPy array, and then after that I just close the original data source because I don't need it anymore. Generally with rasteria, if you open something, you do want to eventually close it. All right, and then since this is an 8-bit image, I define it as 8-bit. So up to this point, it's a NumPy array. So then I use the from NumPy method from Torch to convert it into a PyTorch object. And then I convert it into float and divide by 250 to rescale the data from 0 to 255, or from 0 to 255 to 0 to 1 as a float. And then if I'm going to apply any transforms, the transforms are applied, and then lastly I return the image and the associated label. In this case, in contrast to like a semantic segmentation problem, the image is going to be an image represented as an array with height, width, and channels, and the label is going to be just a value, right? So it's not going to be an image; it's just going to be a single value or index that represents a category. Okay, so and then that just gets returned together there, and then again the length function just gives you back the length of the data frame or the number of samples. All right, next thing I do is I use Torch Vision to define some transforms just to do some data augmentation to potentially improve the model. Note that for some of the other examples I use albumentations. That works really well for semantic segmentation. This is a lot simpler, so I just stuck with Torch Vision. And this is simpler because we only have to transform the image data. We don't have to do anything with the label since it's just a label and it's not like a mask. All right, so basically what I'm doing here is I'm applying some random horizontal flips and some random vertical flips, and then the P there is like the probability of that happening. So again, it's just some data augmentations. Okay, and then once that's defined, then I create my training set, and I apply my transforms, and I create my validation set, and I also apply, I don't apply the transforms since we don't need those for the validation. So the inputs here is the training set, and the validation set, so these are both data frames, and then the folder where the images are stored, same folder, and then the transforms. So let's just go ahead and run everything up to that point and see what we have. I think we stopped here. There we go. So we see here that it pushes back this data set with, again, those same lengths that we had above. Next thing we do is we initiate the model. So this, I have a decent GPU, and these are pretty tiny chips, and there's no associated mask. It's just the scene labeling problem. So I played around with the batch size, and I found I was able to set the batch size pretty high and get this to run. So I ended up using a batch size of 200. That was good partially because this is actually a fairly large training set, so I set the batch size high so we don't have a lot of steps. Okay, so there we initiate the data loader. The only real key thing there is the batch size, feeding it the data set. And since I'm on a Windows machine, I just set the number of workers to 0 since it doesn't really work very well on Windows. Okay, there we go. And then I want to just look at the data. So here I do batch next, iterate, and then I get the images and labels and then just print those. Again, this is just a check to make sure we're getting the shapes that we'd expect. Note that every time I run this, I get this error. I guess it's a warning. It says no geotransform GCPS or RPCS defined. So what that means is that there's no projection information associated, or like geospatial projection information associated with all the image chips. They're actually just little, PNG files with no geospatial reference information. And since this is rasterio and it's designed to read in geospatial data, it's flagging an error there. So anyway, that actually doesn't really matter in this case because we don't need the projection information. So that's fine. If you were reading something in that had projection information and you're getting that error, then you probably want to look into it and see what the issue is. Okay, so here's our shapes. So we have 200 for 2828, so that's the image. So that's the batch dimension, so 200 samples. 4 is the channel dimension, so red, green, blue, near infrared, and then your height width dimensions. Note that raster automatic, whenever you read in data into a NumPy array, its format is already channels height width, which is what PyTorch expects, as opposed to some of the other libraries which do height width channels. So that's why we didn't have to change or permutate the channels there, or the dimensions. Okay, and then the labels are just 200 samples with one dimension, and we can see here that the image is defined as float 32-bit, and the associated labels is an integer 64 or a long integer. So that makes sense. And here I'm just pulling the first image and just spitting out some results for that. So if we pull the first image, again, we can see it's a 4-band image with 28 by 28 for its spatial dimensions. And then we just get back a single value here. That's why it's empty for the label. And again, same thing. It's we have a 32-bit float for the image, int 64 for the label, which is long integer. The data for the image are scaled from 0 to 1, which we'd expect, and the tensor for the label is 2 to 2. It says there's only one value that's going to have the same min and max, and so this one is index 2, which is whatever the third one or the second is. So as you can see here, that this is the list, so that would mean it's a tree example in this case. Okay, and then here's a little visualization thing just to visualize the data. So this sets up a visualization. Note that we're using matplotlib here, and it expects a different order, so we have to throw the channels last, so that's what the permute does. What this is doing is it's converting that image from a NumPy or a torch image to a NumPy array, and then we're multiplying by 255 to rescale it from 0 to 1 to 0 to 255. And then we're making sure it's set as an 8-bit integer, and then it's going to return that image. So let me run that real quick. Okay, and then we set up an iterator here, and also I did find a little dictionary that explains what the numbers correspond to, and then I just iterate over that to show the image, a subset of images. And you can see that here. So all our examples with their associated labels. So anyway, this is just a little function to visualize the data. Again, it's good to do that because you want to make sure you're getting out what you'd expect, right? If there's an error here, visualizing it can generally help with that. Okay, so now we have our data prepped. Our data loaders made. So now we're ready to actually define our CNN model. So again, this is just a scene labeling model, so it's not a semantic segmentation method or anything where we need to do pixel level. So it'll be a little different from some of the other examples. Okay, so here I'm basically subclassing the module here. I'm creating something called net. That's going to be the name of our model. So what are the key components here are, first, the data are going to get thrown into a 2D convolution process. So it expects 4 inputs and it's going to produce 8 outputs. This 4 is really important because this is a 4-band image. So it expects, since you're feeding it a 4-band image, the original input has to be set to 4. And then it's going to basically produce 8 learned kernels, which again are applied to the image to create the feature maps. We're doing that with a stride of 1 and a kernel size of 3 by 3 and a padding of 1. So we should get back the same array shape of the input. So we'll get back a 28 by 28 output. Okay, and then we do batch normalization there. That can again help with things like overfitting and issues with gradients and whatnot. And then we apply an activation function, and specifically here we're using rectified linear unit. And then to decrease the size of the array, we then apply max pooling with a kernel size of 2 and a stride of 2, and that's going to produce back a smaller image. So basically going to be 28 divided by 2 or 14. So now we're going to have an array of 14 by 14 as opposed to 28 by 28. Okay, and then in the next convolution layer, we feed it an 8, which is because we produced 8 output from the first convolution. So those eight layers get fed in. 16 kernels are produced to generate new feature maps. Again, same size, same stride, same padding. Batch normalization is applied. Rectified linear unit is applied for that for the nonlinear, the activation there, and then max pooling 2D is then applied to again decrease the size of the array. And we're using the same thing, so it's going to decrease the size again by half. So we go from 28 by 28 to 14 by 14, and then to 7 by 7. And then next thing we're going to do is feed that into a linear. So this is like fully connected layer here. So this is the number of inputs. So this spits out 16. So it expects 16, and then we're collapsing it. So 7 times 7 are the spatial dimensions. And then this 6 is important because that's the number of final classes or like nodes that you want. And since there's 6 categories, we set that to 6. And then we define the forward pass here. So self.cnn layers, referencing back to this. Self.linear layers, referencing back to this component. And that's going to return back x. Note this x view, x.size 0, -1. What that's doing is between the CNN, which is producing an array, right? So, for example, the last CNN layer is going to spit back 16 feature maps of 7 by 7 height width. But these linear layer, the fully connected layer, is going to expect a vector. So this is effectively collapsing that or flattening it into a vector of length 16 times 7 times 7. Okay, so that defines the model. So again, we're just defining it here. We're not using it or anything yet. So running that. So there's our model. And then we initiate the model by just simply calling it there. So there we have a model. Next we set the optimizer. So we're going to use Atom here, and I just set a learning rate. Again, you could play around with the learning rate to see if that improves your performance. And what it's going to optimize is the model parameters there. So run that. So that's defined. And then we need a criterion. So what is it going to monitor to try to update the weights? So what's the loss function? So here we're using cross entropy loss, and we're using that loss specifically because this is a multi-class classification as opposed to binary. You know, you could also use some other losses like dice or something. This actually might be better because there's data imbalance here, but I'm just using this as a default. Again, if you were wanting to try to play around with improving the model, one thing you could do is try different loss functions like a focal loss or a dice loss or some type of combination like cross entropy and dice or something. Okay, so that initiates that. Next thing I do is I push the model from the CPU to the GPU. So that's what this is doing. So basically saying if CUDA is available, then push the model and the loss to the GPU. And again, you generally want to do that because if you don't, it's going to be really slow. Okay. So we'll do that, and then last I just print the model just to have a look at it. So let's expand this a bit here. So here's our model. So again, convolution layer, batch norm, rectified linear unit, max pooling, next convolution, apply batch norm, rectified linear unit, and then max pooling again, and then that gets fed into the fully connected layer. So it looks right. Again, key things to look at is like your number of inputs, so 4 channels, number of outputs, and make sure everything lines up. So 4 in, 8 out. Then we have 8 in, 16 out, right? And then again, this is 16 times 7 times 7, or 784 once it's flattened. Okay, all right, and then we also would like to monitor accuracy, so just the % correct. So here I'm defining an accuracy function, so it accepts that the result and the input labels return, since this will be, it returns the index of the correct and then sees if it matches. So that's how we get our accuracy there. Let me kick that back. Okay, and then lastly, we set up a training epoch, so our training loop. So here we're going to train for 10 epochs. We're creating some empty, I guess these would be lists. Yeah, to store our val loss, our val accuracy, our training loss, and our training accuracy. And then we go through the loop. Some of the key things here is, again, we're going through each batch using enumerate there. At the start of each batch, it's going to push the X data, the image, to the GPU, and the target label to the GPU. At the beginning of each loop, we're going to zero out the gradients there. And then here we're fitting the model, modeling against the criteria, and then performing that step. And then what this is doing is basically we're setting up or calculating the accuracy and then printing something. So that's what this is. So basically that's the training part, and then the validation part is here. So we set it to no grads. That's important because we don't want to do any gradient updates or anything, since we're just validating it. That would kind of bias the model, obviously. And then we set it to evaluation mode, and then we go through the process of predicting to the validation samples and printing their result. And then in this case, it's really only going to save the model if it sees improvement in terms of loss here. And then it'll save the model out to our working directory with that name, and it's telling us if it saw any improvement. Okay, and then there we go, model.train. That runs the process. So anyway, that's our loop. I'm not going to run that here. For me, I have this machine with a decent GPU. I ran the model on the GPU, and it still took, I think it was 12, 14 hours. Again, these are fairly. It's not a complex network, and the data sets, each chip is pretty small, but there's a lot of them. There's over 200,000, so it did take some time to crawl through all that. Okay, so that's how I generated the model. So the next step was to do some inference on our testing set, just to see how well it performed on some new data. So again, that's this new SAT-6 infer file here. So again, I'm just pulling in my libraries that I need, setting the working directory, checking to make sure that I have my GPU available, and then again, I'm reading in just the test data this time. Since I already trained the model, I don't need the training data. I don't need to do a training and validation split. Here, I just define the exact same model again, so with the same architecture. Then I initiate the model, and then I load into that model the learned weights from the training process. So I use this torch.load to get that, and then I do this load state dictionary to load in those weights. So now we effectively reloaded in our trained model at that point. And then I just put the model into eval mode, push it to the GPU, print it to make sure it looks all right, and then I can go through and make predictions. So first I set up a variable of the directory here. So this is where all the test chips are, and then I specify the device as CUDA because I want this to run on the device. All right, so then in order to actually make the prediction to each individual chip, I set up a loop here that loops through each row in the data frame, and then eventually does the pre-processing and then the prediction, and then writes out the final classification. So let's step through this. So first off, I just create a tensor with one dimension to store the resulting classification. You can see that got pushed to the GPU, and the data type there is a long integer. Okay, and then this sets up the iterator to iterate over the rows in the data frame. So this process is effectively going to be the same as the process in the dataset subclass, because we wanted the images to go through the same processing chain as the training and validation data did when we produced the model. So basically, we read in the data with rastereo, convert that into a NumPy array. Then we close that, because if you open something with rastereo again, you should close it. Then we take that NumPy array, make sure we define it as an integer 8-bit, unsigned integer 8-bit. Then we kick it into a tensor with the from NumPy. We send it to the device, so from the CPU to the GPU. We convert it to float, and then we divide by 255 to rescale it, so 0 to 1 as opposed to 0 to 255. Then we apply an unsqueeze. That's because the model was trained with a batch dimension, and since this is a single image at a time, we don't have a batch dimension, so we just add on kind of a dummy batch dimension so the shapes match. Then this applies the model, so we predict the image using the model, and the output there will be our logits for each class. And then so we're not getting we're not applying a softmax to get back probabilities. We really don't need to in this case because we just want to get the classification. And then to go from our logits for each class into a final classification, we apply this argmax along dimension 1, and what that's going to do is return the index with the highest logit, which is going to be the class that was predicted. Okay, and then this result, and then we just append that or concatenate it to the result class. Okay, and then once that loops through all those 81,000 samples, then I write the result into the original data frame. So first thing I do is I take that result class tensor, I push it to the CPU, and then convert it into a NumPy array. When I initiate the tensor, it created a one value that I don't need because that's not a prediction. So I just grab values from 1 to the end, where so 1 would be at the second position, effectively just removing the first value. And then I create a new column in the data frame called predicted, and I write those results into it, and then I save that out to a data frame. So real quick, let's have a look at that data frame. So that's in my archive here, chips 2, and this is the result. Note I ran this a few times, that's why we have multiple results here. So we end up with something like this, where we have the sample, the index for or code for the classification, and then the predicted classification, right? So this is the reference and then the predicted. Okay, so I could use something like a scikit-learn to generate confusion matrices and metrics and whatnot, but instead I'm just going to do an R because I really like the assessment metric packages in R. Okay, so I'm going to shift over to this last script, SAT-6 confusion matrix.r, and I'm going to run this. So I'm going to pull in that CSV file that has the reference and predicted measurements for each of the 81,000 samples. And note I'm also setting the dplyr and caret packages here because I need those. And then the confusion matrix function that we're going to use from caret, it wants your categories to be as factors as opposed to numeric. So I'm just converting the class and predicted columns into numeric values into factors. And then lastly, I just run the confusion matrix function on this from caret. So I'm feeding it the column representing the prediction, the column representing the reference, and then I'm using mode everything. It will just generate a bunch of metrics. Okay, so we run that. It saves it to this object CM, and then I'm just printing the matrix here to look at our output. I'll expand this a little bit. Okay, so here's our output. So these are indexes for our different classes. If we go back to this example here, we can look at what number represents each class. So 0 is building, 1 is barren, 2 is trees, 3 is grass, 4 is road, 5 is water. Okay, so that's why we have those 6 categories for the rows and columns. So just looking at this, we can see where we have sources of error. So for example, it looks like there was some confusion between class 3, which was grasslands, and class 2, which is trees, and class 1, which is barren. Class 5, which is water, actually had no classes that were confused with it, which is good. And then we also, again, with barren here, we see some confusion with grassland, and that's the main one, grassland. Okay, so, but a lot of the a lot of the values ended up in the diagonal, which means we actually got a high percentage of these right. So overall accuracy for this was 97.62 or 0.9762 as a proportion. Note that so that basically that means that 97.6% of the 81,000 samples were correctly classified. And there's the kappa statistic. And then here we have the class level metrics. So for example, precision, recall, F1 score. So with this, we can look at what classes were most difficult to map or separate. So it seems like class 4 roads, there was some confusion there. Class 3, let's see, like this one has 1, so that's really good for the water. So just kind of looking at this, it looks like our biggest sources of error were classes 3 and 4 and 0. So building, I guess, grass and road. But overall, this is a pretty good prediction just based on our assessment against these new samples that the model hasn't seen before. That's an example of a scene labeling problem where we're getting back a single label for each image as opposed to a pixel level classification. So we'll look at those pixel level or semantic problems in later examples.